everyone. Let's continue discussion on well-ordered set. Now let's look at these examples. In the previous example, we've shown that actually that this pose set in the previous example. The pose set here is well ordered. So now in this question, we want to show whether the set of pairs of positive integers and the partial order, which is actually defined in terms of the less than or equal relation, is also well ordered. Well, we can make use of our result in the previous example by first of all, we note that we've shown in one of the previous examples that this is a total order. Total order on this. If to be sure, you could check this in more detail, right? Should be pretty easy. Now what you want to focus on is to check whether every subset of this set, so C plus times C plus, has a least element. So that's what we want to check. Now so let's do that, right? So let A be a non-empty this is every non-empty subset, right? So let A be non-empty and A is a subset of this. Now because A is a subset of set of pairs, then A is a set of pairs, right? So therefore we could write that actually A is equal to B times C, where B is a subset of C plus and C is also a subset of C plus. Now since set of positive integers and this relation is well ordered, by definition of well-ordered set, we know that B has a least element, so is C, so does C, right? So both B and C have a least element. So note, of course, here B and C are not empty, right? Because A is not empty. Now so let A be the least element of B and small b is the least element of C. So our claim is that A comma B is actually the least so let me just use a different letter. Let B be the least element of capital B and let small c be the least element of capital C. So our claim is that B comma C is the least element of the set A, which is this. Now, well, to check that, let's say, suppose of course we want to check that B comma C is less than or equal to any other pair in A, right? So suppose you have a pair, say D comma E in A. Now then we know that D is in B and E is in C, right? Since we know that B is the least element of B is the least element of this capital B, we have that actually B is less than or equal to D. Yeah. Now we have two cases. Then case 1, if B is less than D, then B comma C is of course less than or equal to D comma E. Yeah, by our definition of the partial order here. Now case 2, B is actually equal to D, right? If B is equal to D, then since C is the least element of capital C, we have that actually C is less than or equal to E. Yeah, so B is equal to D and C is less than or equal to E. So we conclude that the pair B comma C is also less than or equal to D comma E. So indeed that B comma C is the least element. Yeah, so we have the least element, yeah, of the set A. So that's the answer for the second example. How about the third example? Is the set of integers Z and the usual less than or equal relation a well-ordered set? Well, here, we know that this less than or equal sign is actually a total order on set of integers, right? So this could be easily shown by checking the reflexivity, the antisymmetry and transitivity, as well as the total property. Now what you want to check, is it the case that does every non-empty subset of set of integers have a least element? No, the answer is no. Well, take Z itself, right? Yeah. Z is obviously a subset of itself and it's not empty. And Z itself is not empty. But Z set of integers doesn't have a least element, right? So because if you look at the Hasse diagram of Z, you could have so it would look like this, right? So 0, 1, 2, and so on. Sorry, let me just do it here. So you have 0, 1, 2, and so on, and you have -1, -2, and so on. So the Hasse diagram goes down infinitely. So this is not a well-ordered set. So for our next example, then the question is, can we define a relation R on Z such that Z becomes well-ordered? Obviously we cannot use, so here in this case cannot use the usual this, right? So we need to use another relation R. So the idea is that, so if you want to make a chain like this, so you have 0, 1, and then -1, and then 2 and then minus 2 and so on. So this is our idea, right? So we want to make this chain, yeah, create this chain. So how do we create this chain? So the idea is to, how do we define a relation so that we could have this chain, right? So the idea is that we define a function, or we sort of map this to z plus, yeah, map to z plus, yeah, because we already know that set of positive integers together with the less than or equal relation is well ordered, yeah. So map to z plus, so essentially you get, maybe you get 1 2 3 4 5 and so on, right? So what is our mapping? So define f a function such that f on z to c plus, such that f n is equal to 2n plus 1 if n is greater than or equal to 0, and then sorry, I forgot. This is what we want to make. Let's take a little bit here. So this is minus 1, and then 1, and then minus 2, and then 2 and so on, right? Yes. So 2n plus 1, yeah, and then if not, then if n is less than 0, then minus 2n if n is less than 0, yeah. So first of all, let's have a look at this function. F is well defined, right, on all n integers, right? Clearly, right? It doesn't, meaning that for integer n you don't have two different values of f. And of course f is injective, yeah. You could see that that if f is injective because if because if fn is equal fn, yeah, then actually, well, you would have that m is equal n. You could check this, right? Because this is, for example, in the case m greater than or equal to m let me, okay, so, or in other words, yeah, if m is not equal to n, then fm is not equal to fn. This could be easily seen, right? So if m is not equal to n, say m and n are both greater than or equal to 0, then you have 2m plus 1 or let's say, without loss of generality, you would assume this, then 2m plus 1 is bigger than so let me write down. So m 2m plus 1 will be bigger than 2n plus 1, right? So you have this, right? Also, if m is less than n and it's less than 0, then you have minus 2m is actually bigger than minus 2n. So yeah, it's just not the same, right? And of course, is if m is bigger than or equal to 0 and n is less than 0, then of course fm is 2m plus 1, yeah, which is odd, and fn is minus 2n, which is even. So it won't be the same, right? So it is injective. So now let's use this and to define a relation R. So we define R such that a comma b from integers will be in the relation if fa is less than or equal to fb. Now we need to show that this is actually a total order, yeah. It's actually a total order. So is it total order? Well, is it reflexive? The answer is yes, clearly, right? So if a is less than or equal to a, sorry, if fa is obviously equal to fa, so a is less than or equal to a, yeah, or in other words, a comma a is in the relation. Is it antisymmetric? Well, the answer again is yes. So you have two cases. If suppose a comma b is in R and so is b comma a is in R, so we have fa less than or equal to fb and fb is less than or equal to fa. Since fa comma fb is positive integers, are positive integers, then this would have that fa is equal to fb. And since f is injective, we would have that a is actually equal to b. Now transitivity is clear, yes, yeah, because if a comma b and c comma and b comma c is in the relation, then we have fa is less than fb is less than fc, so fa is less than fc, and therefore a comma c is in the relation. Is it total? Well, yeah, well, obviously yes, yeah, because fa and fb are well defined in Z plus, and of course this relation is total order. Now what remains is to show that every subset of Z has a list element according to this R, right? So the next one is does every subset of Z has a list element according to R? Now the answer is actually yes, but let's show this, right? So let A be a subset of Z, a set of integers, and A is not empty, right? So if A is not empty, then let say X to be an element of A. Oh no, so then there is at least then we could define a set FA as follows. So FA is the set of all B set of all X positive integers such that X is equal to F small a for some A in A. Now this set is a subset of Z plus, and which is well ordered by this, right? So as a consequence, FA has a list element, right? So say call it C, so list element C. Now we know that C is in FA. C is in FA, so there is a Y such that there is a Y in A such that of course C is equal to Fy. Now C is the list element, so therefore C is less than or equal to D, which is F of Z, yeah. Sorry. So D less than or equal to D for all D in FA, yeah. So now because of that, and C is actually Fy, and D here is actually Fz, and each D here is such that that D is equal to Fz for some Z in A, right? So now so what we want to show is actually claim is that actually Y is less than or equal to Z for all Z, right? So this is our claim, right? So the idea here is to use the fact that uh, that that actually also we note that f is also surjective. Yeah, yeah, because uh, there is no yeah. So f is surjective, right? This is you could easily check this, right? Hence f is bijective. Hence hence uh, y is the list of element C for all C is in A, because C is less than or equal to F C, yeah, for all C in A. So that's the answer for the example. Now, with that, that's examples of well ordering, and now we look at how this is useful in mathematics, because the well ordering is used to establish that the fact that principles of induction is valid. So in fact, you could have a generalized induction where the statement holds for every element of a well-ordered set, so not just for elements of n, right? Yeah. And the what you learn in discrete mathematics 1 course, the principle of induction, the standard principle of induction is just a special case of this generalization. So the principle of well-ordered induction is stated as follows. So given S a well-ordered set with this less than or equal as the corresponding total order, then the statement Px is true for all x in S if the following statement holds. So we just need this statement, inductive step. So for every y in S, if Px is true for all x is less than y, then Py is true. Now, we don't need to establish the base case of induction, because the inductive step is already, when the inductive step is established and x0 is the least element of a well-ordered set, then there is no x in the set for which x is less than x0. Hence, the premise of the induction step vacuously true, and consequently px0 must be true, or must be vacuously true. So how do we use this to prove some results? So for example, we have a statement theorem that every integer n greater than or equal to 2 can be written as a product of one or more primes using well-ordered induction. So that is, we want to show that this statement Pn n can be written as a product of one or more primes. Yeah. Now we just need the inductive step, right? So suppose let's check again the induction. So we want to show that for every y in S, and S here is set of integers greater than or equal to 2, that if Px is true for all x less than y, then Py is true. So we want to show the inductive step, if Pm holds for all m less less than n, then Bn inductive step. This is to show, right? Bn also holds. So suppose Bm holds for all m less than n, yeah, and m comma n is element of integers, and m comma n are greater than or equal to 2. Yeah. So if n is already prime, then we're done, right? But if n is composite, then n is actually a times b, where 1 is less than a comma b less than n, right? So by induction hypothesis says that PA and PB hold. Yeah. Now that means A and B can be written as a product of one or more primes. That is A is equal to P1 times P2 times so on times PM not PM PK, and B is Q1 times Q2 times up to QL, where P1 up to PK and Q1 up to QL are primes, and then K is and L is greater than or equal to 1. Yeah. Now that means, what does it mean? It means that, well, of course, that means N is equal to AB is equal to P1 times P2 times PK times Q1 times Q2 times up to QL, and this is a product of one or more primes. So we established the statement. Yeah. So with this is just very simple well-ordered induction. So we don't need the base case here. Now, in the next topic, we will talk about upper bounds. So let's stop here and we continue in the next video.